Welcome back to calculus. The concept of the limit gives us information about how a function behaves near a certain point. Not at a point, but near it. And we've looked at examples of estimating limits of a function given the graph of a function. And that's certainly a good way to look at things. But in some cases, we want more precision in our estimate for a limit. And in that case, using a table of function values is actually a more accurate, or can be a more accurate way of estimating a limit than just using the graph. So I wanted to, in this short video, show you how you can use Desmos to create a table of function values, and then from that, estimate the limit of a function. So let's see what it involves. Suppose we had an example like this one. In this example, we want to estimate the limit as x approaches 0 of the function sine of 4x divided by 7x by constructing a table of values. Our estimate should be correct to at least 4 decimal places. So this is a problem in which using a table of values is a really good idea because of that 4 decimal places of accuracy that's required. It's hard to read off 4 decimal places of accuracy from a graph, but with a table of function values you can do it. And as I mentioned, Desmos is a good way to build that table of function values. So let's go to Desmos. I've actually already got a graph open here. The very first thing we want to do is give Desmos the function that we're interested in. As you might remember, we're interested in sine of 4x over 7x. So I'm going to say, let's let f of x equal sine of 4x divided by 7x. And there you see it. And of course, Desmos goes ahead and plots the graph. And you could actually use the graph to do the estimate. Of course, as I mentioned before, that 4 decimal places of accuracy might be a bit of a problem just looking at the graph. So we're going to build a table of function values. Now for a limit problem like this, right, where x is approaching 0, that means we're interested in values of x that are close to 0 but not equal to 0. And so what I want to do is create a table consisting of some x values that are approaching 0 but not equal to 0, and then just see what the f of x values look like and see if there's any trend that I can spot as x gets closer and closer to 0. So we'll begin by creating the table. In Desmos, that's easy. Go over here to the plus button. That's where you can add various items to your list here. And I want to add a table. So I'm going to select that menu item, and you see the table pops up in Desmos. This one has 2 columns, x1 values and y1 values. x1 and y1 are just the variables that he uses by default here. We don't have to take those. I want my x values to just be x values, so I'll change that. And then my y values, I actually want my y to be f of x, right? So I'll just put in f of x there. So that is telling us what the table is going to be filled with. Now we can put in an x value here, and like x equal 1, and immediately we see the f of x value. It's minus 0.10811. So what we want to do here to evaluate this limit is let that x value approach 1 and see if the corresponding f of x values approach any definite number. So I'm going to do that here. We started at 1. I'll take 0.1 as my next value, right? Because that's closer to 0. And I see a different f of x value. Now it's 0.5563 or so. Keep approaching 0, so I'll have 0.01 now. Notice that my f of x value has changed, but not quite as much this time. Now it's 0.5712 and some change. Let's keep on approaching 0.01. Sorry, 0.001. And now we have 0.57142, right? You can see the convergence of the f of x values happening here. It looked like by the time we're at 0.001, right, it looks like I could say definitely that the first 3 digits of the limit are going to be 0.571. I need 4 digits of accuracy, so I need to keep on doing this until I get that 4th digit to settle down and stabilize, right? So 0.0001 gives me 0.57142856. So it actually looks like I do have it now to 4 decimal places. The 0.5714 looks like it's staying constant, right? We could try one more a notch closer. So now I want 1, 2, 3, 4 zeros, then a 1, and now we're seeing, oh yeah, we've got at least, 1, 2, 3, 4, 5, 6. Looks like we got maybe even 7 digits of accuracy now. It looks like the limit from the right, and again, why from the right? Because now my x values are approaching 1 from the right, through values that are bigger than 0. So I've got x approaching 0 from the right in this table. For the limit to exist, we need to look at the values approaching 0 from the left as well and make sure we get the same behavior. So I'm going to need another table for that. I'm going to just add it in a new little line here. So I'll add a table. Again, I want x values in column 1, and I want f of x values in column 2. And now I want to approach 0 from the left. So I could start with x equal minus 1, right? And I can read off my f of x value. And I'll do the same kind of thing, minus 0.1. And I'm looking to see if those f of x values are converging to any specific number. Now I need minus 0.01. Okay, I'm kind of seeing the same thing. It looks like the 0.5 has settled down, but the second digit hasn't. Minus 0.001, 0.5714. This is looking very familiar. Maybe do one more just as a safety check. Look at that. I'm getting the same answers roughly, actually to quite a few digits as I got before. 0.57142856. If I added one more notch of closeness, minus 0.1234 I'm getting the same things approaching from the left as I am approaching from the right? Same things approaching from the left, that would be this table up here. We're looking at a limit that looks like it's about 0.5714 to 4 places of accuracy. So from the first table we made, we basically could conclude that the right-hand limit is 0.5714, right? From the second table, we could conclude that the left-hand limit also looks like it's about 0.5714, and therefore we could conclude that the two-sided limit has a value that we would estimate at 4 decimal places of accuracy to be 0.5714. The way that we would sort of state this mathematically, that the second table was looking at values of x approaching 0 from the left, and we got to 4 places an estimate of 0.5714. The first table we made was values of x approaching 0 from the right, and we also got that same estimate, right? So that means that we would estimate that the two-sided limit at 0 is approximately 0.5714, and we believe our estimate has 4 places of accuracy there. So Desmos and its ability to make these tables of function values is very helpful for estimating the values of limits numerically, like we're doing here. And as I mentioned before, you're free to use Desmos on your homework assignment, so I highly encourage you to do so. I hope this has been helpful. If you have questions, let me know as always, and we'll see you back here next time.